Hello to everyone. This is Shantan Kumar, Assistant Professor, Department of Mathematics, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. The subject is matrices and calculus. The topic we are going to discuss that particularly on the definition and terminology module 2, that is eigenvalues and eigenvectors, the diagonalization of a matrix. Regarding this one, we are going to discuss the today class, that is the definition terminology. In the previous sessions, we discussed that clearly that each and the topic wise, that is a video lectures are did that is eigenvalues and again the eigenvectors and again particularly the Cayley-Hamilton theorem and diagonalization of a matrix, and again the theoretical part is covered, and moreover that is the problems and again the question banks are also clearly we discussed in the previous sessions. And today we are going to discuss that few definitions are occur, that is eigenvalues and eigenvectors and diagonalization of a matrix and including the Cayley-Hamilton theorem. Just only that discussion, that is a definition terminology. That means sometimes it is a problems are also occur that we need to discuss that properly. Within the short time we need to complete that. Here, first of all, what is the syllabus of this is the module 2. And again here, under this syllabus, it is covering like the eigenvalues and eigenvectors and their properties, and without proofs are also, and Cayley-Hamilton theorem without proofs, verifications, and finding the inverse and powers of the matrix by Cayley-Hamilton theorem, the diagonalization of the matrix. These are the topics are occurring in the module 2. We are going to discuss that based upon this, there is a definition and terminology. Here, what is the characteristic equations? That is also we need to discuss, that is a definition point of view, how to define the characteristic equations. And it is a, for example, A is in square matrices A11, A12, A13, A21, A22, A23, A31, A32, A33. This is the any square matrix. And corresponding to, we need to assume any, that is unit matrix, that is I is also 3 by 3, that is 1 0 0 0 1 0 0 0 1. And also that an identity matrix, it is a corresponding the lambda be any scalar. That means it is assumed that actually it is a 3 by 3 matrix, and similarly we need to consider any 2 by 2 matrix or 4 by 4 matrix, and corresponding that unit matrix also we need to assume that lambda be any scalar conditions. And again based upon this A comma I comma L, and again here for example A minus lambda I, that means it is a matrix notation based upon that, that is A minus lambda is called, that is a characteristic matrix. And similarly based upon this one we need to find out the determinant. That is also point of the definition wise, it is a characteristic polynomial. That means if it is asking like that any characteristic polynomial, we need to find out the characteristic matrix to finding the det value. That is a characteristic polynomial. And next one, the characteristic equation. Whatever that above the characteristic polynomial, if it is finding that is equal to 0, that is a equation format, that is called as the characteristic equation. That means these are the related to one by one the terminology. One is the characteristic matrix, characteristic polynomial, characteristic equations. These are the one by one the definition point of view from the given matrix. Under this is the eigenvalues to finding the equations. Next here it is a definitions wise clearly how to define the characteristic matrix with the example like that, like based upon the 2 by 2 matrix. For example, it is a, let A be in a square matrix of order n, and again here then the matrix A minus lambda I, that means it is a characteristic matrix of the given matrix, that is a corresponding lambda, it is called as a characteristic matrix. For example, it is a 2 by 2 matrix, we need to assume that is nothing but where I is also the square matrix of order n, that depend upon the one matrix you need to assume that is a lambda be any scalar. But one example, A is any matrix, that is a 1 minus 2 4 comma 1. It is a consider any matrix, and with the help of that A minus lambda is a matrix, that is corresponding like that subtraction from the diagonal elements 1 minus lambda minus 2 and 4 1 minus lambda, and based upon this one whatever you obtain output, it is a matrix, that is a characteristic matrix. And again the characteristic polynomial, that means same above the first one, whatever it is obtained, it is a matrix of the characteristic. Then if it is finding the determinant, that means det of A minus lambda I is called, that is a characteristic matrix of the like polynomial of the given matrix A. That means A is a matrix like that. Delta of A minus lambda is nothing but whatever you calculating this one, it is delta of A minus lambda. You obtain this is the equations. Even it is a cross verification with the help of the law. 2 by 2 is nothing but lambda square minus s1 lambda plus s2 is equal to 0, like that s2. That s1 is a trace of the matrix and s2 is the determinant of the matrix, and it is s1 is nothing but it is a diagonal element should be 1 plus 1. That it is nothing but it is a minus 9. That is the meaning of it is a lambda square minus 2 lambda plus 9. And further characteristic equation, same whatever the characteristic polynomial by equating is equal to 0, that equation you obtain that is equal to is called as a characteristic equation of the matrix. That means whatever the same equation we obtain that is equal to 0 terminology, that is called as a characteristic equation of the matrix. These are the one by one the interlink like a characteristic matrix and characteristic polynomial characteristic equations. These are the definition point of. And next one, define the eigenvalues. The eigenvalues is nothing but whatever the previous one definition, it is the data of A minus lambda I is equal to 0. By solving that equation, for example, it is a 2 by 2 matrix, we get the values. The values are called as a eigenvalues. That means scalars which are multiplied with vectors which are in same direction. That is not like that. The data of A minus lambda I is equal to 0. We get that according to the lambda value. It is a 2 by 2, you obtain the lambda 1 comma lambda 2. And eigenvectors means the eigenvectors is nothing but whatever the x is equal like that lambda x, and with the help of this one we need to consider lambda x minus lambda I into x is equal to 0, and which is the a minus that is a lambda I, you need to take common x is equal to 0. It is nothing but with the help of that equation you obtain the finding the eigenvectors. That is nothing but a minus lambda I into x is equal to, that is a 0 condition. That is the meaning of eigenvectors of a matrix A is a vector represented by a matrix X such that when X is multiplied with the matrix, then the direction of the resulting matrix remains the same as the vectors of X. That is nothing but we need to remember according to X is equal to lambda X is the condition where X is a non-zero eigenvector, lambda is a corresponding particularly eigenvalue, A is the given matrix. State the characteristic matrix, same like that. Data of a box of A minus lambda I is called the characteristic matrix. What are the other names for the eigenvalues? That means sometimes the eigenvalues are also called as indirectly. It is the proper values or latent values or something, characteristic values or something eigenvalues. Like these are the some particular values. There is a character roots or proper values or latent roots, also known as like eigenvalues, characteristic values are also like other phenomena. State the latent values for identity matrix of order 2. That means based upon that 1 comma 1, like latent identity matrix, because of the matrix is I is a 2 by 2, because of the matrix is I2, that is nothing but 1 0 0 1, and based upon one of the property, the matrix is the unit matrix are also, that is eigenvalues are the diagonal elements, and based upon this one, it is order of the matrix is 2 by 2, therefore the eigenvalues are also that is 1 comma 1 is matrix. Next, what is a spectral matrix? Spectral matrix is also nothing but it is a like a matrix is a said to be spectral matrix. It is a set of like eigenvectors. It is a set of eigenvectors. Sometimes it is called as a spectral. And again, the other terminology it is a spectrum. Spectrum. The spectrum is nothing but it is a collection of eigenvalues. Collection of eigenvalues is called as a spectrum. Spectral is nothing but the resulting the eigenvectors, set of eigenvectors. Sorry, it is a spectral. State the model matrix. The model matrix is nothing but the diagonal form of the given square matrix. Real matrix D is called as a, sorry, it is a like it is required. The set of eigenvectors are nothing but it is a model matrix, and again it is a like a diagonal form of the spectral matrix. That is nothing but D is equal to, that is a P inverse in D into P. That D is called as whose the diagonal elements are diagonal elements are eigenvalues. And again, P inverse into AP, whose the diagonal elements are the eigenvalues, then the resulting diagonal matrix is called as a spectral matrix. That means for this is the collection of ordered model matrix is nothing but the P, and again it is denoted by the symbol is a P. It is like x1 and again x2 and again x3. The spectrum is nothing but that is a like collection of eigenvalues, and again the spectral is nothing but then the resulting diagonal matrix is called as a that is spectral matrix. When eigenvectors are linearly independent, the eigenvectors are whenever it is linearly dependent is nothing but that depend upon the n eigenvector length is linearly dependent if the matrix which is the columns has a zero determinant. Not only vector size, not only it is columns are zero, sometimes it is rows are also zero. That condition is said to be that is linearly dependent. That means indirectly the data of value is nothing but zero. But as per the definition of the eigenvector is nothing but that is based upon the collection of the eigenvectors, that is a column wise, and but here that one of the column it is a zero. But actually the eigenvector is always it is a non-zero eigenvector, it is satisfied. When eigenvectors are linearly independent, when eigenvectors are linearly independent is nothing but that is if the eigenvalues are in distinct eigenvalues and automatically it is distinct eigenvectors, and automatically distinct eigenvectors is nothing but the linearly independent of the matrix. That means it is not equal to zero. Non-zero determinant. That means the data of is not equal to zero. That is the meaning of the linearly independent. Or in case it is a distinct eigenvalues or distinct corresponding eigenvectors. That is a linearly independent. State the Cayley-Hamilton theorem. The state the Cayley-Hamilton theorem is nothing but every square matrix satisfies its own characteristic equations. Every square matrix satisfies its own characteristic equation. That is the meaning of the Cayley-Hamilton theorem. That means we need to find out according to what is the data of A minus lambda is equal to 0. We obtain based upon that lambda q minus s1, for example, it is a 3 by 3 lambda square plus s2 lambda minus s3 is equal to 0. Here it is a replacement of lambda is equal to that is a. Then the equation is reduced to lambda cube minus s1 a square plus sta minus s3 is equal to 0. That equation is satisfied after calculating that given matrix A and again A square and also the corresponding A cube. We need to replace the equation is satisfied. That means that is the meaning of every square matrix satisfies its own characteristic equation. Is the Cayley-Hamilton theorem statement. If the problem if the matrix is a 2 by 2 or 3 by 3 or 4 by 4, any number of an order of the matrix. State the uses of the Cayley-Hamilton theorem. State the uses of Cayley-Hamilton theorem is nothing but based upon the Cayley-Hamilton theorem, we need to apply like finding the like powers of the matrix, and moreover it is the inverse of the matrices. The two are the majorly that Cayley-Hamilton theorem like uses higher order negative and also positive powers of the matrix. That is inverse and also the powers of the matrix. That is the meaning of here the uses of the Cayley-Hamilton theorem. That means with the help of this one, we need to find out A power n and also A inverse of the matrix. That to find out based upon the two applications or two uses of the Cayley-Hamilton theorem. And if all the eigenvalues are distinct, then their eigenvectors are. That means according to the property, when you are calculating that eigenvalues are different and also the eigenvectors are automatically it is linearly independent of the matrix. That is a data of the value is not equal to 0. That is a linearly independent of the matrix. State the demerit of Cayley-Hamilton theorem. The demerit of the Cayley-Hamilton theorem is nothing but at the time of the Cayley-Hamilton theorem, we need to generally it is using that the pre-multiplications are required, pre-powers of the matrices, and to find any powers of the matrices. These are the like demerits of the Cayley-Hamilton theorem. State the demerit of the matrix with the two equal eigenvectors. That means state the determinant of the matrix with the two equal like two eigenvectors. That is 0 because of the determinant of the two equal eigenvectors are, that means it is like x1 and also x2. It is a condition. If it is both are same, that is x1 comma x2, that it is equal to automatically 0 is the conditions. Since x2 is equal to given, that consider one other vector is also x2. Since x1 is equal to, that is x2 is the eigenvector. Define the characteristic equation for the matrix A. Define the characteristic equation for the matrix A. That means whatever the characteristic matrix, and with the help of the characteristic matrix, we need to find out that is the equation is equal to 0. That is a delta of A minus lambda equal to 0, where lambda being a scalar value. That is a characteristic equation of the given matrix, where A is any square matrices, and again we need to assume that I is also the corresponding the unit matrix of order I A, and again I is also unit corresponding the unit matrix of the given matrix, and again lambda is any scalar matrix, and we need to find out the data of A minus lambda equal to 0, that is under the 2 by 2 or 3 by 3 based upon the equations. Under the 2 by 2, as you know that is a like 2 by 2 matrix, that is a lambda square minus s1 lambda plus s2 is equal to 0, and again under the like 3 by 3 matrices, it is a lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. These are the like according to like under the 2 by 2 and also 3 by 3, that is a short methods to finding the characteristic equations. State eigenvalues of an orthogonal matrix. The eigenvalues of an orthogonal matrix are also always it is a unit matrices. That is based upon the unit matrix is nothing but it is a plus or minus 1. If that is nothing but if it is a matrix, is A is a matrix, according to A is a orthogonal matrix is nothing but A into A transpose equal to I. Therefore, A into A transpose of the matrix is also nothing but A square is equal to I. Then A is nothing but it is a plus or minus 1 is a value. Because of the unit matrix that is a 1, therefore A is equal to plus or minus 1. Therefore, it is a unit modulus of the or the eigenvalues of the orthogonal matrices. Value of the sum of the eigenvalues is equal to, that means whenever the given matrix, to find out the eigenvalues with the help of the characteristic equation, while we are going to calculating the major property, it is the sum of the eigenvalues is equal to the trace of the matrix. That is a trace of the matrix. While we are calculating n in the 2 by 2 or 3 by 3, we need to get that clearly, that is a sum of the eigenvalues is equal to the trace of the matrix. Define the product of the eigenvalues is equal to, and this is also the property of the eigenvalues. It is when you are going to calculating the powers of the eigenvalues, that is product of the eigenvalues, if it is required to cross verification, that is a determinant of the matrix. That is meaning of the determinant of the, that is the trace of the matrix is equal to sum, and the determinant of the matrix is equal to the product of the eigenvalues of the given matrix. For example, if 1 comma 2 comma 3 are the eigenvalues of A, then the eigenvalues of square matrix, that is also nothing but power. It is nothing but it is a powers of the matrix. That means they are asking to find out what is a square. That means A is given 1 to 3, that is A is equal to 1 comma 2 comma 3, then A square is nothing but 1 square and 2 square and 3 square. That is the meaning of 1 comma 4 comma 9 are the squares of the eigenvalues. If 1 comma 2 comma 3 are the eigenvalues of A, then the eigenvalues of 2A. That is nothing but based upon that Ka property. Here eigenvalues of A is equal to, that is 1 comma 2 comma 3. It is asking like the 2A, that is 2 into 1 comma 2 comma 3. It is nothing but 2 comma 4 comma, that is 6 are the eigenvalues of the 2A matrix. If 1 comma 2 comma 3 are the eigenvalues of, then the eigenvalues of inverse, that is nothing but the property of the A inverse. Here A is equal to 1 comma 2 comma 3, the inverse of the eigenvalues is nothing but 1 by 1 comma 1 by 2 comma 1 by 3. That means it is 1 comma 1 by 2 comma 1 by 3. And similarly 1 comma 2 comma 3 are the eigenvalues of A, then the eigenvalues of A plus I. That means A is given that 1 comma 2 comma 3, and I is also the corresponding, that is a 3 by 3 matrix. The eigenvalues are 1 comma 1 comma 1. Therefore, the addition of A plus I is nothing but it is a 1 plus 1, and again 2 plus 1, and again 3 plus 1 is nothing but 2 comma 3 comma 4 are the eigenvalues of the given matrix. These are the some properties based upon that. It is sometimes it is a definition terminology point of view. They may be asking to find the solutions. If 1 comma 2 comma 3 are the eigenvalues of A, then the eigenvalues of A minus 2I. And it is also same like that above. It is 1 comma 2 comma 3, and again I is also corresponding. It is 1 comma 1 comma 1, but it is not like that A plus. It is a minus 2I. Therefore, first you need to calculate A 2I. That is a 2 into 1 comma 1 comma 1. It is nothing but 2 comma 2 comma 2. And here A minus 2I. A minus 2 is nothing but 1 minus 2, and 2 minus 2, and 3 minus 2. It is nothing but minus 1 comma 0 comma 1 are the eigenvalues of A minus 2I. Therefore, these are the conditions based upon the properties we need to observe here. How to identify the like eigenvalues, that is indirectly it is a definition terminology. The problems. Define the necessary condition for a matrix A to be diagonalizations. That is the necessary condition is nothing but it must have a linearly independent eigenvectors. That means whenever the matrix is said to be like the diagonalization according to the property and again problematic time also we discussed previously, whenever the different eigenvalues are satisfied, that like indirectly there is a different eigenvector, therefore different eigenvector is nothing but automatically the condition is a diagonalization of a matrix. That is the main fundamental the condition. The distinct eigenvalues is nothing but the different distinct eigenvector. The distinct eigenvector is nothing but it is a diagonalization is a existed. Next, state all the matrices diagonalization or not. It may not possible sometimes the diagonalization because it is depend upon the repeated eigenvalues and different eigenvalue. It should be the diagonalization is existed. Therefore, all the matrices need not the diagonalization of the matrix because of sometimes it may be the eigenvalues are repeated. At that time, we need to check that according to AM and GM. That AM and GM it is sometimes it is both are same. That is a non diagonalization, and that condition AM is not equal GM, then only it is a diagonalization. At that time, it is not we can't say the matrices, all the matrices are the diagonalization of a matrix. The computation of power of a matrix become faster if it is a diagonalization. Yes, it may be, it is a true conditions. Because of it is a d is equal to that is a p into d power of n into like that condition, based upon that it is a diagonalization of the matrix, it is a diagonalization. Power some matrix faster if it is a diagonalization. Yeah, that is absolutely true condition. It is existed. Yeah. The determinant of the matrix whose the eigenvalues are 4 comma 2 comma 3 is given by the determinant is nothing but while we are going to observing these are the 4 comma 2 comma 3 is the eigenvalues of A matrix, that is a given the matrix A. They are asking the determinant as per the property. The determinant is nothing but it is a like data of A, it is a required is nothing but it is a data of A is nothing but it is a product of the eigenvalues are required. That is 4 into that is 2 into 3, that is nothing but 36 is the like sorry not 36, it is a 24 are the eigenvalues of the determinant. Condition is satisfied. Yeah, define what does a zero eigenvalue mean. If the eigenvalues of a zero is any matrix, then automatically the inverse does not exist because of the det is equal to 0. That is not invertible. Because if any one of the eigenvalues, for example, it is lambda 1 comma lambda 2 comma lambda 3. Here one of the eigenvalue is 0, for example 0 comma 1 comma 2, that is inverse is does not exist. Because of it is inverse is adjacent of A by that is a data of A, that it is adjacent of A is a possibilities, the data is nothing but it is 0, therefore it does not exist the conditions. That is the meaning of define what does it 0 eigenvalue means. It is a inverse does not exist the conditions. Like these are the like examples like definition terminology point of view under this is the model 1, that is eigenvalues and eigenvectors. And finally I think this is the last one, which is that our eigenvectors are orthogonal. Yeah, it is not always orthogonal because of based upon the like repeated eigenvalues, it is normalized is required. Based upon that our eigenvalue or eigenvectors like orthogonal, it is not a like condition because of A into A transpose equal to that is I, and based upon it is a not orthogonal condition. Sometimes it is a not possible. Like these are the some of the definition terminology point of view. Under this is the model 2, that is eigenvalues and eigenvectors, including the Kelly Hamilton theorem problems, like it is a diagonalization of a matrix. I hope everybody understood. Based upon these are the definition terminology. And in next session we'll go to discuss that is a model 3, that is a functions of several variable, like mean value theorems are also that we are going to discuss in the next session. Thank you. I hope everybody understood. Wish you all the best. Have a good luck. And again, if any doubts are under this is the definition terminology, please give the reply under in this following the link only. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.